Hello, am I audible now?
Yes, sir.
Okay, good. Oh, I think Rajiv was asking in the chat about the sound. Actually, that's why. So, I think you might have already gone through the second second week's entire module and the uh, hello, Rajiv, Rajiv Arora. Rajiv, can you try reconnecting? I guess uh, there might be some issue because here. Yeah. Hello, Rajiv. I think now it must be audible to you. Uh, okay, then I think Rajiv won't be able to join us, and he's having some problem on his connecting end. So I'll just start the class for today. So welcome everyone. This is the session two, and I think you guys have already gone through your second week's lectures, and you might be already seen. You might have already seen the modules, and might be familiar with all the thermodynamics and whatever was taught there. So the assignment due is also, I guess, maybe tomorrow or day after tomorrow. So by now you might have already answered all of them. So this is like a more refresher on whatever the questions were encountered. And if you have any doubts, you can ask me. And this will be a good preparation for you for your upcoming certification exam if you have applied for it. So yes. So we'll be facing a few questions today, and this is an interactive live session, and we can go through and we can see if you have any doubts or anything regarding that. So our first question is, how do thermodynamic principles influence? One second, one second. Rajiv, I think since you're connecting with the phone, that's why it's showing some issue because you're not also visible in my window. Prashant and Suprabha are visible, but you are not visible. So maybe there is some issue because or else you are accessing through multiple devices. Okay, then I'll just start discussing the problems. How do thermodynamic principles influence the process of polymer crystallization and the determination of polymer crystal energy? So we have four options here. By regulating the activation energy for crystallization, by altering the molecular weight distribution of polymers, by modifying the glass transition temperature of polymers, and by affecting the chain conformation and intermolecular interactions. So what happens is that first question which might arise in your mind is how can polymer be crystal? So and what is polymer crystallization? So what happens is that as we discussed in the previous class, polymers are formed with multiple chains of macromolecular chains, which consists of the monomer units repeating in a fashion. So these long polymer chains their orientation and how they are arranged in the entire polymer molecule is what gives the polymer its crystallinity. The higher the crystallinity of a polymer, the more stiff and harder it becomes, and that in itself causes the polymer to become slightly more brittle than what it is in its natural conditions. So in the polymer, you might have seen that the main quality of the polymer is that they are quite flexible because uh, all polymers are not entirely crystalline, and all polymers are semi-crystalline in nature, which means that they have some amorphous and some crystalline phases inside them. And that's what makes the polymer quite flexible. So the thermodynamic principles which influence the process of polymer crystallization and determines the polymer crystallinity is dependent on the fact that how these crystals are formed. So how does that happen is when you have molten polymer or a polymer melt, as in like for example, you take polyethylene or you can take polypropylene and you take it to the melting point, a higher temperature, and you prepare a melt of it. Okay, uh, and I'm talking about raw polyethylene or raw polypropylene. You melt it and you take it to a higher temperature. You stir it down, and then what you do is you start cooling down this batch of molten polymer. What happens is that as you are cooling down, the thermal energy which is stored inside these polymer chains, which is causing them to move around, is losing. It's going down. So what happens is these polymer chains start arranging themselves in orderly manner or orderly fashion. So the rate at which you're cooling them down also determines the polymer crystallinity. So what happens is that their chain conformation is getting affected by the way you're cooling it down. Okay. So what's happening in that case is, one second. Hello, Rajiv. I think still we are not able to join with you. Okay, so what happens is that the chain conformation and how the chains are arranged as you're cooling down the polymer melt itself is what determines the polymer crystallinity. On top of that, the intermolecular interactions which are present inside it. Intermolecular in the sense like there are two types of forces which are present inside the polymers. That is intramolecular forces and intermolecular forces. Intramolecular forces occur within the same polymer chain, and intermolecular forces occur between two polymer chains. So what happens is that when you're cooling down a polymer, since it's molten, the chains are free to move. And as you're cooling it down, these chains they become stiff. And as you're cooling it down, they arrange themselves in a orderly manner. And that orderly arrangement is what determines the chain conformation. On top of that, the intermolecular interactions between two polymer chains, such as the van der Waals forces which are present inside them, also determine how the uh, polymer crystallinity will be shaped. If you have better intermolecular interactions, the arrangement will be much more close packed, and because of that, the chain conformation will be better and your crystallinity will be high. Uh, Alteration of molecular weight distribution of polymers will not guarantee or does not in any way guarantee that the crystallinity of the polymer might be high because if you're increasing the molecular weight, which basically means that you're increasing the uh, polymer second.
Sir, alteration of the molecular weight may affect the MFI, like the melt
Yes,
index,
melt flow
but not
index.
not the crystallinity.
Yeah, it won't affect the crystallinity. Because basically, by increasing the molecular weight, what is going to happen is the chain gets longer. And if the chain is longer, uh, sometimes it might not arrange itself in a close pattern. And it will cause entanglements between the chain. These entanglements, what they do is they increase the viscosity of your polymer a lot. That viscosity increase will what it will do? It will increase your MFI because MFI is basically rheology based, and there you have the viscosity. So that's why your MFI will be affected. The third one is by modifying the transition temperature of polymers. For a given polymer, you won't be able to modify its glass transition temperature. You can do that by addition of any kind of filler material or some other copolymer which can join together and form a new polymer. But then the nature of the polymer itself is changing. So modification of glass transition temperature is not the option. So and by regulating the activation energy for crystallization will not change much of it.
Sir, like gas transition temperature is the property of pure polymer itself. Like
Hmm.
we can't change it thermodynamically, but while adding some additive or doing some co-monomer or something like that, we
Yeah,
can do some juggling in that. But original polymer glass transition with playing with thermodynamics, we can't do.
yeah, we can't do that. And in a similar manner, by regulating the activation energy for crystallization, also won't you can't do that because for a particular polymer, the crystallization activation energy will remain the same. The only way to modify it by either by bringing some chemical change or changing the process in itself. So that is not the correct answer. The last one, that is the by affecting the chain conformation and the molecular interaction. is the correct one. That is on the basis of the thermodynamic principles which will affect the polymer crystallization. Next, we have which thermodynamic principle governs the prediction of the phase behavior and the phase transitions in a polymer blend and composites. So we already have a famous phase rule also by this name, that is the Gibbs phase rule. And what are the ways in which this thermodynamic principle governs the prediction of the phase behavior is that what happens is using the Gibbs free energy, it will determine the phase behavior and the phase transitions in polymer blends. So in polymer blends, if there are two or more polymers blended together, and if they are forming some composite, these polymer blends and their thermodynamical properties are very different than the single homopolymer in itself. So that will account to the Gibbs free energy of the polymer and the mixture itself. What happens in this is that the spontaneity of the reaction and the spontaneity of the blend itself is what will be affecting, or the extra free energy, whichever is present, will be governing the thermodynamic principle. Okay, Rajiv, I think now you might be able to listen to me because I can see that you have joined properly. And yeah, maybe because you were joining with the phone, that's why I was not audible. And there was some issue with that also, I guess. That's why. So, the thermodynamic principle which governs the prediction of phase behavior and phase transition in polymer blends is the Gibbs free energy. Moving on to the next one, we have in context of polymer processing, which thermodynamical concept uh, in the context of polymer processing, which thermodynamic concept explains the influence of temperature and pressure on the solubility of polymers in the solvents. So we have different laws right here, and you can see that I have described a law through a picture right here, and this is nothing but the Raoult's law. So in context of polymer processing, Raoult's law is quite evidently popular for describing the influence of temperature and pressure on the solubility of polymers in solvents. So what happens is that when is a polymer properly soluble in a solvent, and when can the solvent uh, easily remove the polymer chains which are clumped together inside a polymer mixture. So that will be governed by the Raoult's law in itself. As you can see the description of it, the mole fraction mole fraction and the vapor pressure of the polymer solvent mixture in itself can be useful in determining the solvent's ability to dissolve that particular polymer. And because of this, we use Raoult's law in context of polymer processing to describe the dissolution of the polymer in any solvent. Next, we have the which thermodynamic property is crucial for determining the miscibility of polymer blends and assessing the compatibility between the polymer components. So, which thermodynamic property is crucial for determining the miscibility of polymer blends and assessing the compatibility between different polymer components? So we have different definitions right here. First, we have the entropy, which just describes as we have seen in the previous slide in itself, that for any kind of polymer blend or any kind of phase transition, free energy is very much required. So what happens in this case also is that uh, to check the thermodynamical property for the miscibility of polymer blends, mixing of the polymer blends is done, and the miscibility can only be determined by observing the free energy which is present inside the polymer itself. Okay, so what happens in this case is that since polymers are quite viscous, the maintaining the pressure pressure constant and the pressure constant is quite difficult, and because of that we have different four options right here. So we have entropy, enthalpy, and internal energy. Internal energy of the polymer in itself won't be determining the uh, miscibility conditions because the effect of temperature will also be there, and the entropy in itself also won't determine that. It will be a combination of all those, which can be determined by the Helmholtz free energy. And as you all know, the Helmholtz free energy formula is H is equal to U minus Ts. So uh, that comes from the definition of Helmholtz free energy. That is the internal energy minus the sum of the the multiplication of the temperature and the entropy. And that is because Helmholtz energy is defined at a constant volume and temperature, whereas the Gibbs free energy is defined at constant pressure. So in case of polymer blends, since we are blending them together, the volume constant uh, criteria fits in that because we won't be able to maintain the pressure in itself. And that's why Helmholtz free energy is much more preferred for determining the miscibility of the polymer blend. So next we have it's a basic question. What does the concept of entropy represent in thermodynamics? So what does the concept of entropy represent is we have four options, and clearly we can see that the second one, that is the measure of disorder or randomness in a system, which is caused by the movement of the molecules in itself, is what determines the entropy, which is represented in the thermodynamics. So next one we have uh, what does the chemical potential of a substance in a system indicate? So the term which has been introduced right here is the chemical potential. So in basic terms or basic terminology, chemical potential means that the potential difference. I will talk it in a definition sort of way that it's the potential difference which drives forward the chemical reaction. Or for an analogy, you can imagine that you can imagine some kind of concentration gradient which can cause the mass transfer, or you can talk about some thermal gradient which causes the heat transfer. So because of that, for a chemical reaction to occur, you need some sort of chemical potential or some sort of difference in the difference in the potentials of two chemicals or polymers or anything for the system to move on its own and react. So because of that, what happens is how that can be defined is that can be defined by the spontaneity contained inside the system. And to best describe that, we have the definition of free energy. So the change in Gibbs free energy when 1 mole of substance is added to the system. And you can see the definition which has been given right here. We have the nu I is equal to dou G by dou N for an I species. So you can see right here that the chemical potential nu I is a measure of how much the free energy of a system changes by dG. That is the change in Gibbs free energy. If you add or remove a number of dn particles, that we can consider that as mole also the particle species I while keeping the number of other particles in the system same. So what you're doing is consider you have two systems, two isolated systems. One is I and one is J. So you can keep the J constant and add the I in it, and then you can see the change in Gibbs free energy when 1 mole of the substance is added to that system. So based on that, the definition of chemical potential is what is defined. That the change in Gibbs free energy when 1 mole of substance is added to the system. Next question. What is the main difference between fugacity and activity coefficient in thermodynamics? So here we have the terms of fugacity and activity coefficients in thermodynamics. So what happens here is that we have the four options right here. Fugacity is a measure of a substance tendency to escape from a mixture, while activity coefficient represents the change in Gibbs free energy when 1 mole of a substance is added to the system. Now, just now we have learned that the second part of the statement is not true because the definition that gives free energy when 1 mole of a substance is added to a system is nothing but the chemical potential. So that definition is not true. But the first part is true that fugacity, in a sense of manner, is a measure of a substance tendency to escape from a mixture. Or you can correlate it with the partial pressure of that uh, partial pressure of the substance in itself. So that's why first option is wrong because the activity coefficient definition is not wrong, right? Next, we have the fugacity is the total amount of substance present in a mixture, while activity coefficient is the measure of a substance tendency to escape from a mixture. Now you can clearly see that uh, this definition is not right, as the fugacity definition is not accurately described here, and the activity coefficients definition has been mixed with the fugacity in itself. The third one is fugacity is used to describe ideal solutions, while activity coefficient is used for non-ideal solutions. So right here, we can see that this definition, how it works is fugacity in itself is used to describe uh, ideal solutions. Why is that? Because whenever you are equating a system's tendency to a substance tendency to escape from a mixture or a system, that can be only described by its, you know, the partial pressure in itself. And how does that occur is that if the substance in itself, if the substance has a high partial pressure for a purely ideal condition, you can see that fugacity will be equal to the partial pressure of the substance itself. So this expression right here, which says phi I is equal to Fi by P, Fi is your fugacity and phi I is the fugacity coefficient multiplied by the P. So what happens in this case is if the substance is you say that ideal, your Fi will be equal to the P in itself. So that's why fugacity is used to describe ideal solutions, while activity coefficient is used for non-ideal solutions. What happens is that if your system is not described by fugacity, this basically means that it's non-ideal in nature. So how much it is deviating from the ideal conditions can only be defined by the activity coefficient. So that is described by the activity coefficient. Next, we have the fugacity is only applicable to gases, while activity coefficient is applicable to both gases and liquids. That is not true, since fugacity can be described for both solutions, liquids and gases. So that's why the third option is the correct option. Next one we have the Flory-Huggins theory is primarily used to predict the glass transition temperature of polymers, determine the mechanical properties of polymer blends, estimate the solubility of polymers in different solvents, or analyze the molecular weight distribution of polymers. So what's happening here is Flory and Huggins have proposed a theory which is basically used for which is basically made on the fact that polymers are based on a rigid lattice model in which the polymers are made up of R segments, like R is an arbitrary number or arbitrary value of segments. So based on this, what happens is based on this, the Florian-Huggins theory says that this can be used for any system where polymers are being mixed. So we have an expression here delta G mix is equal to delta H mix minus D delta S mix. So here you can see that this is a Gibbs free energy description of a system which is being mixed together. So the Flory-Huggins model, what it says is that this can be defined by the rigid lattice model for a particular polymer, and how that polymer is going to interact with these solvents is what defines that model. So what this is the second expression which has been given here. Delta G mix is equal to RT N1 ln phi 1 plus N2 ln phi 2 plus N1 phi 2 and xi 1 2. So here, what are the parameters involved here is delta G is your change in Gibbs free energy. R is your gas constant. T is the particular temperature at which the polymers are being blended together, or sorry, the polymer and the solvents are mixed together. N1 is the mole fraction of your solvent, and ln phi 1 is the volume fraction of the solvent in itself. N2 is your mole fraction from the polymer, and phi 2 is the mole fraction from your volume fraction from your polymer. And N1 and phi 2 are then, as I described earlier, and xi 1 2 is the mixing parameter for the mixing activity parameter for the polymer and the solvent described by 1 and 2. Now, how does this play into picture is that some solvents are described as alpha solvents or beta solvents. And what does alpha solvent and beta solvent mean is that that is based on the ability of that particular solvent to dissolve that particular polymer. Because every polymer will not be able to be dissolved in different solvents because uh, it might have some affinity to some aprotic solvent or maybe polar solvent, non-polar solvent. So based on that, you have to describe this. So that's why the Flory-Huggins theory then estimates this by using the thermodynamical definition, using the rigid lattice model for describing the polymer as R segments and dividing them. And then these formulas are used to estimate the solubility of the polymers in different solvents. So based on the change in Gibbs free energy, you'll be able to easily tell if that particular polymer is be will be able to be dissolved in that solvent or not. So based on that, you are estimating the solubility of polymers in different solvents. So since today's topic was thermodynamic based, I've only discussed a few questions, and I think most of them will be much more helpful for you to solve your assignments. So you can ask me any doubts if you have.
What want to ask? Hello,
Hello, yeah, yeah, you can ask.
sir. If we are blending some nanomaterials, suppose we are developing a film based on the nanocomposite material of polyethylene conducting polymer with the help of the polyvinyl alcohol. Then
Okay.
how we can estimate the uh, free energy? How we can go for the calculation of delta H or gives free energy for this blending process. We
You
have
have
taken a solution of PVA
okay.
in a water
PVA
because
in
the
water.
PVA is the water soluble
Hmm.
polymer.
Okay.
We have taken the low molecular weight of the PVA. There
Hmm.
are the two things. One is one PVA is higher molecular weight will be go for the hot water mixing, and some light molecular weight
Hmm.
PVA will be the cold water solutions.
Okay.
We have developed the cold water solution of the PVA
Hmm.
with the help of the water. 2 3
Hmm.
hours we have to run the PVA and we have developed the solutions. After that, we are doping the nanocomposite material based on conducting polymer. Then what will the process
Hmm.
we are in we go to the thermodynamic properties, how we have to analyze that.
Okay. So let me just ask if I've understood this properly. You're dissolving PVA in water first of all. Okay.
Yes, yes.
Okay. Polyvinyl alcohol you're
It will
dissolving
be
in.
it may be some exothermic reactions. It will be heat the vessels.
Hmm. Correct. So we can first of all estimate the solubility and we can find out what is this PVA water system, how much energy or what is the entire energy of that system, mix system. We can get that. Okay.
Nay, how we have to calculate that, or how we have to develop a paper based on the thermodynamics paper, thermodynamic properties.
Properties
Okay,
of that, right?
uh, as we are discussing here, delta S, delta G,
Hmm.
entropy, these things, how we have to calculate, how we estimate it.
What are the you are saying? Sorry, the experimental method.
Yes, how we have to set up the equipment, we have to analyze that
Hmm.
parameters.
Hmm. Yes. So, actually, it's a very good question. And first of all, I'd like to give my background in itself that I'm actually not dealing with polymers in that capacity, as you have asked me the question about. But I can actually I can take it down and maybe I'll get back to you about this because it's quite a complex problem which you have given me right now. Because the experimental methods through which it can be measured might be different, and it might be more than maybe the scope of my knowledge which I have right now.
Sir, within few lectures, we have some word we come to know about the polymer calorimetry. So
Hmm.
might be that method could help about that. But if you share some video, something linked about that, so in upcoming lectures, so we can get
Yeah,
to know
yeah,
that.
sure, sure, sure. I can share you the videos about that polymer calorimetry, and it's basically a form of the differential scanning calorimetry only used to investigate the response of polymers to heating. So it's based on that basically.
Sir, I just want to more clear about my understanding about the glass transition temperature,
Yeah.
just in reference of polyethylene terephthalate and HDP, if you compare.
Hmm. Hmm. Yes. So what doubt you had with that?
Sir, if you wanted to differentiate between the two plastic like high density polyethylene and polyethylene terephthalate, and
Correct.
with using a property like glass transition temperature.
Correct. Okay. Oh, so you are asking me like the definition of it, basically?
No, sir, not a definition, but just like that, if we want to differentiate between two plastic like PET and HDP, so
Hmm.
how just like both having a different application, so
Yes.
might be some property that differentiate because of this property, it
Hmm.
can be used for a bottles, and because of this property, it is used for the cap. So like
Yes.
that.
Okay. Yeah. Actually, a polymer which is having quite high glass transition temperature will have much more glassy behavior, or you can say stiff behavior, because you know that polyethylene uh, in some forms its Tg is in negative. You know that, right?
Yes, sir.
Yeah. So Tg in that case is negative. So, and that's the exact reason why polyethylene is very flexible in the what you can say in the room temperature. Polyethylene is very flexible actually, and that is one of the reasons. And you can see another thing is that the PET, right? PET is used for making bottles, and that is also dependent on the fact that the Tg of polyethylene third phthalate is around 65 to 80 degrees Celsius. So it lies in that range. Okay. So it has much more higher rigidity than your polyethylene. So based on that, definitely these two are different molecules. The Tg will be different. So you can differentiate based on that. Okay.
Yes, sir. And there was a one topic like amorphous and crystalline polymer.
Hmm.
So
Yeah.
I'm just saying what I understand from that.
Hmm.
Like in lectures, there was a statement like amorphous polymers are getting softer with increasing a temperature, but
Yes.
in crystalline you will get a melting point, like suddenly you change in volume. But in amorphous we don't see like that. Am I
Yeah.
right? What
Yes, sir. You
consideration?
are right. You're right. You're right. Why this is happening is because in crystalline polymers, the chains themselves are packed together. Okay, the van der Waals forces and the intermolecular forces are quite high. So that's why they don't react to temperature that quickly. That's why the moment you keep increasing the temperature, there will be a point where suddenly all the intermolecular forces are overcome and the polymer will melt. It will start melting. Whereas in case of your amorphous polymers, right, as you keep increasing the temperature, it will immediately, since the arrangement of the chains are not that proper, it will immediately undergo the phase change. Okay.
Okay, sir, without any like chemical reaction or something like that, can we transfer a polymer from amorphous to transition state, like amorphous to crystalline or something like that?
Actually, you can change the processing through which the crystallinity can increase because there is a relation called structure processing property relationship. So the way you process a polymer also changes the structure of the polymer. For example, if you have polyethylene in a bulk, uh, it might be very soft and it might not be like that hard. But if you draw it out in thin wires, right, you are increasing the crystallinity of the entire polymer. And because of that, these wires which are manufactured, they are extremely strong in nature. So that way you can do it. But it will only affect the crystallinity like a small bit, but it will have some impact on it, definitely. Other method to if you want to alter the crystallinity is to increase the molecular weight because if the molecular weight is higher, the molecular weight should be higher and the cooling temperature during the crystallization portion of that polymer should be quite slow, the cooling rate, because if you cool down the polymer very quickly, the chains don't get time to arrange themselves and interlock themselves. So if you cool down slowly, what happens is the polymer chains take a ordered fashion and they arrange themselves properly. And because of that, the crystallinity will be much more higher. So the main parameter you have to control is the cooling rate if you are going down from the polymer melt to the real polymer.
Okay.
Yeah. Rajiv, I think I will definitely try to answer your question once I have more context on the entire scenario which you described. PVA being dissolved in water and then the nanocomposite deposition like that. Okay.
Eh, okay, okay.
Yeah, because I think it's more of a like what should I say now? It's more of a research problem which you just described. That's why I think you are working
Okay.
on that. Are you working on that?
Yes, yes. Yes, yes, yes.
Yeah. So I'll try to find something and I'll definitely answer your question. Okay.
I am working on some nano composite materials,
Okay.
titanium dioxide, and then I'm thinking ki how we have to find out the thermodynamic properties so that we have to write some paper.
Hmm. So first of all, the you are mixing the TiO2 into the PVA water solution.
No, no, I'm not just working that we are developing the first and the nano composite material of polyethylene and titanium dioxide.
Okay, polyaniline.
Yes,
Polyaniline. Okay.
because the polyethylene is the conducting polymer
Ah,
and it comes under the category of the p-type material,
okay,
and
P-type material.
titanium dioxide will comes under the category of n-type of material.
Hmm.
So we are thinking about to develop the some uh, pn material, pn
Hmm.
composite material that will be the under the semiconductor material.
Okay, so you're trying to manufacture a semiconductor material. Okay. Okay. Yeah.
After that we are developing a film with the help of the pva,
Huh.
so that semiconductor material will be come into the pictures. We have to use in the electronic purposes, semiconductor materials, photoelectric material,
Yeah, yeah.
like that.
So it's like a substrate, kind of.
Yes,
Okay. Okay. Got it.
that film is required of the PN type material. So
Hmm.
how we have to go for the film? We have to require some insulating material so that film will be developed in between that.
Okay. Film will be developed in between that. Got it. Okay.
Likewise, a base to develop a film on that. Like, am
Hmm.
I right?
Yes, 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 yes.
Yes, yes.
PN composite material will be developed on the PVA base.
PVA base.
Yes.
Okay. So, will it be able to withstand high temperatures?
Yes, it will be work at high temperature because the titanium dioxide up goes to the 600 degree centigrade, 500 degree centigrade, and polyethylene will be the 200 degree centigrade. If we
Hmm.
develop that composite, it will be change some glassy glassy temperature of the composite material.
Okay,
It
okay.
depends upon the size of the titanium dioxide material.
Hmm.
It will be the 8 nanometers or 20 nanometers or 40 nanometers or 60 nanometers. That
Okay,
depends which
okay,
type of the titanium dioxide nanomaterial will be developed and we are utilizing.
okay, okay.
That is the thing.
Hmm.
So
I'll
that
yeah. So this PVA film, it will be able to withstand quite high temperatures, right?
yes, it will be the depend upon the which type of the PVA material you are utilizing.
Hmm.
Low molecular weight, high molecular weight, because the PVA will be dissolved into the hot water. So
Ah,
that will be the high molecular weight material. So your selections will be on the base of the PVA. Which
but
type of the PVA you are interested to
hmm.
utilizing.
Okay.
Because if you are interested the high conductivity,
Hmm.
then the molecular weight of the PVA should be the lesser, so that insulating material will be lesser, insulation will be lesser.
Yeah,
If you want to high temperature, then we go for the high molecular weight, then it will be
definitely.
the insulating with behavior. So it
Yes.
all the optimization should be required. Still till now we have studied that
I think your
different type.
optimization will be mostly dependent on the molecular weight of the PVA, right?
Yes, I am saying na ki which type
Hmm.
of the PVA you utilizing. So I have
Yes.
read out all the papers.
Ah.
Still I am thinking about that as we are discussing here ki how
Hmm.
we have to find out the thermodynamic property. So then we are thinking ki some work can be done on this so that we have to or some parameters we can collect ki gives free energy, entropy, then we
Okay.
have to modulate that all the thing
I
come
mean,
into the picture.
this PVA polymer, you can do a DSC analysis of it, right? You can
No,
get the
we can go for the ideal graphs.
hmm.
DSC will be ideal graphs, TGA will be मतलब
Yeah,
DSC है
you
TG.
will get TG melting everything from DSC itself.
हाँ, yes, yes.
Yeah.
But it gives the na high more precise when we are doing the practicals.
Hmm.
Then how we have to analyze the temperature, how we have to find out cell that
Hmm.
study, so
Yeah.
that we have to develop on data.
Correct. You're right. You're right. So,
If we have to develop some on data,
hmm,
then calculation should be easy.
easy. Yes.
Yes, that is
Another
the thing.
thing is that you can do the one thing that you can get two samples of one low molecular weight and one high molecular weight, and based on that, you can see, you can
But
find the optimized value, maybe.
yes, but there a number of things that na कि number which type of equipment with you, how we are doing the work, all
Hmm.
these decisions should becomes.
Yes, yes. Actually, quite a complex problem you have, I think.
Yeah.
Like, are you PhD which year?
I have done the PhD on the nano composite material.
Oh, so you have already finished PhD.
Yes, but
Oh, okay,
still I am interested to do these works.
okay, okay, okay. That's very good.
PhD never completed uh, in life.
Yeah, yeah. You're right. You're actually right. Exactly. PhD is never completed. So, like, are you working right now?
No, presently I am not working.
Okay, okay, okay. Okay, then I'll try to find out how can we find out the various properties of this PVA mixture, any kind of polymer, I would say, and how to get these properties such as gives free energy and all those things. Okay,
Yes, yes.
okay, then I think today's class is over. That those are the all questions which I had to discuss. So you might be able to answer the assignment questions from the video.
If you give some address, then I will send you some samples. If you have some facility in the labs for the
Yeah.
testing, then you have
Actually,
to do that.
we already have a DSC in our lab, differential
So
scanning.
I will send some samples. You have
Okay.
to try to find out.
Hmm.
Then we will discuss about this something.
You already know my name, and I'm in IIT
Uh,
Kharagpur. So,
you will give me your and my mobile number is 94102
okay, 94102
61921. You
94102
give
6192.
Rajiv Arora.
Rajiv. Yeah.
You give
Okay.
me your address. I will send you some samples.
Yes. Sure.
Then you have to analyze that. Then we try to write some papers with you, sir.
Yeah.
Actually, I have not seen the IITs, but if
Okay.
you give the some works, so it will be happening.
Yeah. I mean, you are actually the problem which you have given to me. It's actually very interesting, and I'll try to discuss this with my supervisors. Okay.
That is thing we have to develop. Actually,
Hmm.
I am interested to develop some solar material.
Solar
Photo
material.
catalyst.
Yeah.
Photo. Are interested to use titanium dioxide, which is photo catalyst.
Hmm.
That can be developed with the help of the conducting polymers. Can we develop some photo materials like that?
Hmm.
I'm
Okay.
thinking about that. I'm
Okay.
collecting data,
Hmm.
but I have no facility of the testing.
Okay. Okay.
So I have written to many persons about this, but no response is there.
Okay. Then
I have
definitely.
simple a small lab in the chemistry lab
Hmm.
where I have to work at that. So,
Okay.
but testing facility is required, and if we have to go for the testing in the private sections, and then the cost is very high.
Yeah. Very high. It's very high. Correct.
So there is a limit.
Hmm. Yeah. I mean, definitely sure. Then I will discuss this problem and I'll get back to you. Okay.
Okay, you have to give me the address. I will
Yes.
send the samples
Yeah. Yeah. Sure.
on
Sure.
this WhatsApp. This message, I will send you samples. You
Yeah. Yeah.
discuss with the guide.
Hmm.
You will be find the if it is a positive,
Hmm.
then it will be.
Good. Yeah. Sure. Definitely.
Thank you, thank you.
Yeah.
I have taken your times.
No. 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 It's fine. It's fine. No problem. Okay. Then today's class is over. So
Okay, thank you.
yeah.
Okay, thank you, sir.
Yeah. Yeah. Okay. Sure.